We're going to have a look at a very simple process. It's called completing the square. In order to get to it and to show its potential use, I want to start with a simple equation, x squared equals 9. In order to find out what x is, we would take the square root of both sides. So the square root of x squared is just x, and the square root of 9 is plus 3 or minus 3. Because minus 3 all squared is also 9. So that was relatively straightforward. Both of these two numbers were square numbers, complete squares. What if we got x squared is equal to 5? Do the same again. So we take the square root of each side, x equals, now 5 is not a square number. It does not have an exact square root. But nevertheless, we can write it as root 5, that is exact, or minus root 5. So far, so good. The same process is working each time. Let's have a look at something now like x minus 7 all squared equals 3. How can we solve this? Well, again, this side of the equation, we've got something called a complete square. So we can take the square root of each side. X minus 7 is equal to the square root of 3, or minus the square root of 3. And so we can now add 7 to each of these. So x is equal to 7 plus root 3, or 7 minus root 3. Let's just have a look at another one. X plus 3 all squared is equal to 5. Again, this is a complete square. So again, we can take the square root. X plus 3 is equal to root 5 or minus root 5. And now to get x on its own, we need to take 3 away from each side. So we have x equals minus 3 plus root 5 or minus 3 minus root 5. But what if we got x squared plus 6x equals 4? The problem is this x squared plus 6x is not a complete square. So we can't just take the square root. So in terms of handling something like this, we've got to have a way of getting a complete square. So the process that we're going to be looking at is called completing the square. The sorts of expressions that we had before were like this: x plus a all squared, or x minus a all squared. So that's what a complete square looks like, one of these two. So let's multiply this out and see what we get. So this is x plus a times by x plus a. And we do x times by x, that gives us x squared. And we do a times by x, which gives us ax. And then with x times by a, which again gives us ax. And then at the end, a times by a, which gives us a squared. And so with x squared plus 2ax plus a squared. Now I can do the same with this one. X minus a times by x minus a. And it's going to give very similar results. X times by x will give me x squared. X times by minus a minus ax. Minus a times by x minus ax. And minus a times by minus a plus a squared. So tidying up the two middle bits, minus ax minus 2ax, and then plus a squared. So this is what complete squares look like? They look like one of these two. Well, can I make this look like a complete square in some way, shape or form? If I compare this with this, what is it that I see? Well, perhaps one of the things I might like to have is this written as just a function, x squared plus 6x minus 4. And let's not worry too much about solving an equation. What we want to concentrate on is this process of completing the square. So, I'm going to take this quadratic function, x squared plus 6x minus 4. And I'm going to compare it with the complete square, x squared plus 2ax plus a squared. Now, the x squareds are the same. 6x, 2ax. I've got to have these two terms the same. They've got to match. They've got to be exactly the same. And that means that the 6 has to be equal to 2a. And of course that tells us that the a is equal to 3. So, if I make a equal to 3, then I've got plus a squared on the end, plus 9. So, I can look at this first bit and I can make it equal to that. So let's write this down. X squared plus 6x minus 4 equals x plus 3 all squared. Remember, this is x plus 3 all squared. Now I'm replacing the a by 3. Now what more have I got? Well, I've added on a squared, so I've added on 9. So I've got somehow to get rid of that. Well, let's just take it away. Minus 3 squared. And then I can keep this minus 4 at the end as it was. So now I have x plus 3 all squared minus 9 minus 4 gives me x plus 3 all squared minus 13. So I have completed the square. I've made this bit a part of a complete square. And I've done it by comparing the coefficient of x with one of the two standard forms. And I saw that what I had to do was take half the coefficient of x. Let's have a look then at another example. X squared minus 8x plus 7. And I want to write this so it's got a complete square in it. Well, one of the standard forms for the complete square that we had was x squared minus 2ax plus a squared. And I want to make these two terms the same. So again, we can see that the a has got to be 4, because minus 8 is minus 2 times by 4. So we've got x squared minus 8x plus 7 is equal to x minus 4 all squared. So I've ensured I've got the x squared, I've ensured that I've got the minus 8x, but I've also added on a squared. So I've got a squared too much. So I must take away 4 squared. And then I've got the 7 that I need to add on to keep the equal sign. And so this is now x minus 4 all squared minus 16 plus 7. So that's x minus 4 all squared minus 9. Let's take one more example. X squared plus 5x plus 3. And let's see if we can follow this one through without having to write down the comparison. In other words, by doing it by inspection. What do we need? We need a complete square. So we need x, and we look at this number here, the coefficient of the x term on this left-hand side. We want half that coefficient. So we want 5 over 2, and we've got a plus sign, so it's got to be x plus 5 over 2. If we were to multiply out this bracket, we would be adding on an additional a squared, where 5 over 2 is the a. So we've got to take that away. Take away 5 over 2 squared. And then at the end, we've got plus 3. So this gives us x plus 5 over 2 all squared minus 25 over 4 plus 3. And of course, we'd like to combine these numbers at this end. X plus 5 over 2 all squared minus 25 over 4 plus, now we need to convert these to quarters as well. So 3 is 12 quarters. And now we can combine these, since they're both in terms of quarters. X plus 5 over 2 all squared minus 13 over 4. And we'd leave it like that. This process now seems to be working quite well. But of course we haven't dealt with every kind of quadratic expression we could have, because so far we've only had a unit coefficient here in front of the x squared. We haven't had another number like 2 or 3 or whatever. So let's have a look at what we would do in that case. So we have 3x squared minus 9x plus 50. What do we need to do to begin with? Well, we know how to do this if we've got a unit coefficient with the x squared. So let's make it a unit coefficient by taking out the 3 as a common factor. So that's 3 brackets x squared minus 3x. Now, 50. What are we going to do with this? Well, we divide it by 3 in order that when we do the multiplication, 3 times 50 over 3 will just give us back the 50. And now we look at this thing here in the bracket, because this is now exactly the same sort of expression that we've had before. Equals 3. Let's have a big curly bracket. I'm going to make this, I'm going to complete the square around this, so this is going to be x minus, look at the coefficient of x and take half of it, 3 over 2, all squared. By doing that, we've added on an additional a squared, so we need to take that off. 3 over 2 squared. And then finally, plus 50 over 3. And close the big bracket. 3x minus 3 over 2 all squared minus 9 over 4 plus 50 over 3. And close the big bracket. Now all we need to do now is put these together. And to do that, we need a common denominator, and the common denominator of 4 and 3 is going to be 12. 3, the big curly bracket, x minus 3 over 2, all squared, minus over 12. We need to change the 9 over 4 into twelfths. 3 4s gave us 12, so 3 9s give us 27. Plus, we need to change the 50 over 3 into twelfths. 4 times 3 is 12, so 4 times 50 is 200. And now I've got a little bit of arithmetic to do. Let's just write that bracket down again. Equals 3, the curly bracket, x minus 3 over 2 all squared, minus 27 over 12, plus 200 over 12, and that's the calculation that we need to do here to simplify. 3, the curly bracket, x minus 3 over 2 all squared, plus all over 12, and we're going to take the 27 away from the 200. It's going to give us 173, and then we can close the bracket off. So despite the fact that the numbers were quite fearsome there, we've still ended up with a complete square. And we've automated the process so that what we're doing is looking at the coefficient of x. First of all, we check that what we've got, the coefficient of x squared, is 1. If it's not, we take out the coefficient of x squared as a factor. Next, we check the coefficient of x and we take a half of it. And that's the number that's going to go here inside the bracket. Then we must remember that we've got to take off the square of that number, because effectively we've added it back on. And then the rest is just arithmetic. So, now we've developed this technique of completing the square, let's use it to solve our original problem. If you remember, we had x squared plus 6x was equal to 4. And we chose to write that as x squared plus 6x minus 4 equals 0. So, first we need to check, has it got a unit coefficient? And it has, so we don't need to take out a common factor. Now, we look at the coefficient of x, and it's 6, and it's half that coefficient that we want, so we need 3. So this is going to be x plus 3 all squared. In doing that, we have added on 3 squared. So we need to take off that 3 squared. And now we need to include the minus 4 so that we can maintain the equality of this expression with this one. And it's equal to 0. So x plus 3 all squared minus 3 squared, that's minus 9, and minus 4 equals 0. So we can combine these. X plus 3 all squared minus 13 equals 0. Add the 13 to each side. X plus 3 all squared equals 13. And now we're in a position to take the square root of both sides, because here on the left-hand side we have a complete square. And so this is x plus 3 equals, now 13 isn't a complete square, it's not a square number, so we have to write it as square root of 13, or, remembering when we take a square root of a number, it's plus or minus root 13. Now we take the 3 away from each side, and we end up with our 2 roots. So we take the 3 away, we have minus 3 plus root 13, or minus 3 minus root 13. And so that process of completing the square can be used to help us solve a quadratic equation. But that's not the real issue here. You can see another video on solving quadratic equations. The point is to master this technique of completing the square.